The solver has finished. Here you can see the convergence of shell domain. If you go to the next tab, you can see the convergence of tube domain. Since there are two domains here, we can see the convergence separately. Let us go to the last tab. Here we can see the convergence of tube outlet and shell outlet temperatures. The shell outlet temperature is 341.2 and the tube outlet temperature is 294.54. Both have converged very well. Alright, now we can close Solver Manager and go to CFD Post. Right click Results and click Edit. First we shall see the streamlines. Click this icon to create the streamline. Click OK. Start from the shell inlet. Keep the number of points as 100. Go to color, change the variable to temperature and change the range to local. Click Apply. You can see the streamlines representing temperature. You can also notice the color changes from red to orange. It means the temperature in the shell side is dropping. Here you can see the scale. It is dropping from 353 to approximately 345 or 344 Kelvin. Okay. We can turn on the tube domain to see this clearly. We can rotate this and see. Alright. We can hide the streamline now and go to a new plane. Go to location, click plane, OK. Let us create the plane along YZ direction. Go to color, change the variable to temperature again and range as local. Click Apply and hide this interface region. Here you can see the fluids passing in tube domain as well as shell domain. The colors represent the temperature. In this mid plane you can see only one tube. We can change the plane orientation and see 3 tubes. You can keep this along ZX plane and click Apply. We can see here. Let me show only the tube model. Go to domains and select only the tube domain. Click Apply. We can change the temperature range. Go to color, change the range to user specified. It is varying from 293 to 324. We shall keep around 293 as minimum and 294 as maximum. Apply. We can change it to 295 better. Okay. Here you can see the temperature increasing in the tube side, but it is increasing marginally. That's why I kept this range small. Okay. So always note that when you are seeing a contour plot, you should always check the range of the parameter. Okay. Next, let me show volume rendering. We can hide this plane. Click volume rendering here. Okay. Choose the variable as temperature and change the range to local. You can click Apply. This will show the volumetric representation of flow parameters. Here it is not quite clear. We shall check only the shell domain. Choose shell domain. Go to color. In the variable, you choose temperature with user specified range. Starting from maximum is 353 and minimum you can keep around 340. Click Apply. Here it is better. You can also increase the resolution and change the transparency to see it better. Okay, we can turn off this volume rendering and calculate the exit temperatures as well as heat transfer rate. Go to calculators, function calculator, mass flow average, shell outlet, temperature. Click Apply. Similarly, we can check tube outlet temperature. Next, we can calculate the mass flow rate. Instead of calculating each parameters in function calculator, we can go to table. Click this table icon. Click OK. Here you can write set of parameters and find out the value. First, let us calculate for the shell region. We can first find out the mass flow. Next, temperature inlet, temperature outlet. Next, we can calculate for the tube. Tube mass flow, temperature inlet and temperature outlet. Alright. Go to function, choose mass flow at shell inlet. Enter. It is calculated. We can change the format by clicking this icon. We can hide these units and keep 3 decimals in fixed format. So the value is 0.693, the unit is kg per second. We can copy this and paste here, go to number formatting again and show only the units, remove the value. Okay. Next we can calculate the temperature at inlet and outlet of shell. Go to function, mass flow average of variable temperature, physical locators, shell inlet. This is the input actually, so it is 353.1 Kelvin. It is 80 degrees Celsius. Alright. We can copy this and paste here and change it to outlet. Enter. Similarly, we can copy these 3 things, paste here and change the parameters as tube. Click this. Okay. Next this will be tube. Enter. This is tube. Okay. We can change the format. Go to number formatting, hide the units. We can change the number formatting, select these values, go to number formatting, uncheck show units and keep it as fixed. Click OK. We can also copy this and paste here, select these values, go to number formatting and show only the units. Now you have calculated the mass flow rate and also temperatures at the inlet and outlet for shell and tube domains. Next we can calculate the rate of heat transfer between these two domains. We can copy them and paste it into an Excel sheet. Go to Excel and paste the values. Okay. We know that the rate of heat transfer Q is given by mc delta T. We know the mass flow rate. We can find out the delta T. We have to check the value of C, that is specific heat. The specific heat of water is 4184 joule per kg per Kelvin or per degree Celsius. C is equal to 4184 joule per kg per Kelvin. Let us calculate the heat transfer rate. Q will be equal to mass flow rate into C into delta T. Delta T is 353 minus 348. It is equal to 14,338 watt. We can copy the same value and paste here. We have to point the specific heat here. So here it is 14,377. So both are almost matching. Here on the shell side, heat is transferred out of the domain, and in the tube side, heat is transferred into the domain. That's why the sign is different. We can change the format here. Okay. Next we shall go to CFD post processor and check the rate of heat transfer between the shell and tube domain. Go to function calculator. Area integral of, go to any of the interface region, shell to tube side 1. Click OK and choose heat flux. Click OK. Click apply. Here it is 14,381 watts. So it is matching very well. From CFD, Q is equal to 14,328 watt. Alright, we have calculated the heat transfer rate from both shell domain, tube domain and also from interface region. Here this is from CFD, that is the heat transfer rate occurring between the two domains. Okay, next we shall calculate the log mean temperature difference. We can quickly revise that. The formula for log mean temperature difference or delta theta is given as theta 1 minus theta 2 divided by ln of theta 1 by theta 2, where theta 1 is the temperature difference on one end and theta 2 is the temperature difference on the other end. That is the difference between temperatures of hot end and cold end. Okay, we shall calculate them now. We can copy this. We shall calculate this. Maximize, insert, the symbol is theta 1 and this will be theta 2. Theta 1 is the temperature difference between the hot and cold fluids at one end. So temperature of the shell minus temperature of the tube at the inlet. Similarly, theta 2 is at the outlet. Temperature outlet of shell minus temperature outlet of tube. Therefore, LMTD is equal to theta 1 minus theta 2 divided by ln of theta 1 by theta 2. Okay, this is equal to 56.77. The unit is Kelvin. It can be Kelvin or Celsius because it is a difference. Okay, we have calculated the log mean temperature difference. Okay, you know that we can also calculate the rate of heat transfer from LMTD. The formula is given here. Q is equal to U into A into delta T, that is log mean temperature difference. Here Q is the heat transfer rate, U is the overall heat transfer coefficient, and A is the heat transfer surface area. Here it is the interface area, and delta T is the LMTD. Okay, here we have got Q, LMTD. We can calculate the area from CFD post processor. By this way, you can calculate the overall heat transfer coefficient. Next, let us calculate the A value. It is meter square. We shall go back to CFD post. In the function calculator, you can choose area and choose any of the interface. Here it is shell to tube side 1. Click calculate. The area is calculated. It is 0.263093 meter square. We can copy this. Okay. Now we have got area, LMTD and Q. Next we shall calculate U based on this. U is equal to Q divided by LMTD divided by area. And the unit for this is watt per meter square per degree Celsius or Kelvin. We can keep Kelvin. So the value is 959.3. This is the overall heat transfer coefficient of this heat exchanger. And please note that this value corresponds to the particular flow conditions. It can vary if the flow conditions are changing. Okay. By this way, we have calculated the heat transfer rate from the interface region, from the temperature difference in the shell side and tube side, and all these three values are matching. And from the heat transfer rate, we have calculated the LMTD also. And finally, we have calculated overall heat transfer coefficient U. This is LMTD calculation. Okay. In the next lecture, we shall repeat the same problem after including baffle plates and find out these parameters and compare the results. Okay. Thanks for watching this video. I will see you in the next lecture.